let's get on with the subject matter today, and the subject matter is power. What the hell is power? It turns out that power has something to do with energy, and energy has something to do with mass. So we have all this connection there, right? Um, I've held that no one has any idea what energy is. Okay, and so let's begin there and let's find out what energy is. Then maybe we can find out if anyone knows what mass is. And I'm going to show that according to some of the questions, some of the issues people raised, some of the comments people made, lots of people are still stuck on this mass issue. They have no idea what mass is. And if power depends on energy, which depends on mass, or they're all related somehow, well, the question is whether we're going to learn anything about power. Okay, so this is the subject matter today. So let's begin with an article that came out, okay, the other day. And even though the article was brought up the other day in the beginning of December, first week of December, it dates the idea and the original article dates for about a year ago. Okay, so it's like 1 year old already, but that's irrelevant. The point is what this individual says, what he states about energy. Okay, so let's begin there. Here we have it. So it says fragments of energy, not waves or particles, may be the fundamental building blocks of the universe. He's a professor of mechanical aerospace engineering at North Carolina State University, Larry Silverberg. And this gentleman says that there's something called energy out there, and it's these fragments, the debris of energy that makes up matter. It's not particles, it's not waves, as you've always been told. And remember, he's a PhD, right? He's a professor. Okay? And the article says, this fellow says, matter is what makes up the universe, but what makes up matter? Yeah, good question. What makes up matter? I thought it was atoms, right? And this fellow says, my colleague Jeffrey Eischen and I have described an updated way to think about matter. Whoa, good. We propose that matter is not made of particles or waves. Love that. What is it made of? It was long thought, but more fundamentally, the matter is made of fragments of energy. Okay, and here it is. If you always wanted to know what energy looks like, here we have it. Okay, I want you to see it. There it is. This is what he thinks energy is. These are the lines of energy. Okay, they swirl around, I guess. And he says new mathematics have shown that the lines of energy can be used to describe the universe. Okay, so he's saying that what underlines all matter is energy. Do we know what energy is? Okay, that's the question. Okay, and here you see a dynamic version of energy. I want you to be careful because it's going to run into your eyes. There it is. Okay, you see all that energy just flowing into your eyes. Okay, so this is what the universe is made out of. I guess it's divided in two parts. The bottom half has the energy, and the top half has the stars. This is how they conceptualize the universe. A little surrealistic, but yeah, this is their vision of energy. Okay, so now you know what energy looks like, what it is, and it's fragments of this stuff that's flowing into your eyes or that swirls around, all these lines of energy. That's what makes up matter. And so the question is, what are these lines of energy? Are they physical entities? Because, I mean, they draw them as lines. Whether they come into your eyes or swirl around, they're just lines. So what are these lines? I mean, forget about energy. If energy is just a bunch of lines, we got to go to the line. We got to go to the bottom of the pile and find out, what makes up the energy. What are these lines? It's like saying field. What is a field? Well, field is this region where we have numbers. Okay, but then numbers are not physical objects, so there's no physical object called field. And this is something similar. If energy is made out of all these swirling lines or lines that come straight into your eyes or whatever, what are the lines? Forget about energy. We need to figure out what the lines are. Okay, you have a magnetic field again, lines of force. We need to find out what those lines of force are. Forget about the field. The field is a bunch of lines of force. Now we need to figure out what the lines are. That's the way it works in science and physics. Okay, you can't just say, well, they're just a bunch of lines of force and we just use them to describe the field or something in there. No, we got to get to the bottom of it. We got to find out what those lines of force are. We have to find that needle in the haystack. Okay, that's the way it works. Anyways, we don't have to go too far, and I've shown this before. We have Mr. Feynman. He says it is important to realize that in physics today, we have no knowledge of what energy is. Okay, so he's saying he doesn't know what energy is. Obviously, energy is not a what. It's not a thing, because energy is defined as a concept. It's defined as capacity, the ability. There's no physical standalone object called ability or capacity. So that's where the whole thing ends, because you can't define something as capacity and then say you're going to move the capacity or kick it around, like if you kicked a something. So either we have these lines of energy, which are some kind of, I don't know, some string, some little thread of some kind, right? Or we define the term and say, it's capacity. It's a mathematical concept and nothing but. One of the two. And yeah, because they don't know what energy is, and Mr. Feynman says, well, I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can't possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that. Okay? Tremendous statement from a Nobel Prize winner in so-called mathematics, mathematical physics. So yeah, we don't have any idea what energy is, because energy is not a what. Energy is a mathematical concept. And if it's a concept, it's not a thing. It's not a standalone thing. And so this other fellow, who professor, whatever, who says that matter is made out of fragments of energy, well, that really stretches the imagination, because here we have a Nobel Prize that I'm sure outranks this professor, this good professor, and tells him that there is no such thing as energy. And if you don't know what energy is and you're going to explain everything with energy, then we have a problem. And the problem is what Feynman just said. Nobody understands quantum mechanics. No kidding. If you want to understand it, at least define your terms, or separate the objects from the concepts and say, look, this is an object and this is a concept. So if you're going to talk about an object, illustrate it, point to it, name it. If you're going to talk about a concept, define it. That's how simple it is. But if you don't have a definition and you say, well, it's a physical object, but I can't illustrate it because it's the capacity, then we have a problem. Of course, he's not going to understand anything about the universe, because mathematical physics already has the seeds of its own destruction. Its foundations are rotten to the core. That's what happens. And so what happens? Well, it turns out energy is just another form of mass. Oh my God. So we don't know what energy is. Now we're going to get to mass. Are we going to find out what mass is if mass is just another form of energy? Well, we don't know what energy is. It's not a what, it's a concept. And now we're going to figure out what mass is. Is mass a physical object? Is it a concept? Is it a mathematical concept? What is mass? And I tried to explain a little bit about mass in the last few lectures, but some people are very hard at hearing. They're very hard of understanding. And so let's see if we can go through some of this again. And I'm sorry for those people who have to put up with all this, but I need to clarify some points so that that people at least find out what the arguments are. Okay, mass is a big word, so so is energy, and force, field. Those are very big words in mathematical physics. We need to destroy them. We need to utterly destroy them, because people have the idea that these are physical standalone objects that they can move around. They talk about moving the mass and transferring the energy and stretching the field or vibrating the field. You can't do that, because these are mathematical concepts. Okay? And so, people have these lousy notions in their head, because this is what they were brainwashed. This is what they learned by rote in high school, primarily in high school, and then later on reinforced in college. Okay? I know, because I took a lot of college physics courses, and and it was driven deep inside me, and I didn't, come up to speed until later on when I got out of college. That's when I started doing research. Okay, so here one fellow says, mass is a measure of how much matter, what? How many atoms, right? He clarifies that. Mass is a measure of how much matter there is in an object. How many atoms? Okay, keep that in mind. The amount of matter it contains is measured on a scale, okay? We can then calculate a very close approximation of how many atoms there are. Okay, it's known as a mole. Okay, fine, so we can calculate how many atoms there are. If mass is how many atoms, his own words, right? Then all he's got to do is state mass in terms of how many atoms, okay? According to his own definition, this requires him to state his results in terms of how many atoms. You cannot say that mass is 1 kilogram. You got to say mass is 500 atoms, or 500 units of mass, or whatever you want to call it. Okay, but he's got to state his how many atoms in terms of a number followed by units or atoms or whatever, because that's his definition. That's his notion. So he can't say mass is 1 kilogram. That's my point. Okay, you got to state it in number of atoms, which is what he's stating is the definition. Okay, so We know now what mass is. Mass is the quantity of matter, and it should be stated in number of apples and not in kilograms of apples. Okay, Paul continues. He says, when you drop something from a height onto a scale, it has an acceleration, that is weight. Okay, so he's saying weight is something dynamic. You're dropping it. As it falls, we call that weight. That's what he's saying. When it hits the scale, that is mass. Okay, so hits the scale means now it's stay there. Okay, it's pressing down on the scale. The scale goes no further. We have a static situation, and he's going to call that one mass, which again, what are we talking about? Quantity of matter, which is what he said before. How many atoms? That's mass. Okay, and what he's saying is that weight is something dynamic. Okay, that as the elephant falls, that's weight because that's the pull of gravity on the object. Whereas that once it hits the scale and moves no more, now it's standing still essentially with respect to the scale. Now we call that mass because we can say, well, that's 1 kilogram. That's his notion. So mass is quantity of matter. We're essentially measuring by saying kilograms how many atoms the thing has, whereas weight is the pull of gravity. And of course, the pull of gravity is different on the moon for the same object than it is here on the Earth. Okay, so that's the difference they want to give you. The notion that the mathematicians from Newton all the way to today to Stephen Hawking and passing through Einstein, all these people had the same notion. Okay, so I just want you to understand what they understood by mass and weight. And the example always given is that if you take whatever weight here on Earth, say the grand kilo, used to be the standard of the kilogram, if you took that grand kilo, right, kilo to the moon, it would have a different weight because the pull of gravity on the moon is different than here on Earth, and therefore the weight changed, but the mass, the number of atoms, remained the same. Do we understand each other? Okay, we're saying that the elephant that's falling there, he would weigh different on the moon. The acceleration of gravity on him would be different, even though the guy is the same guy that's sitting on the scale on the right-hand side. The number of atoms that comprise him are just the same. Nothing has changed in the structure, the number of atoms that the elephant has. I hope I'm getting through to someone out there, okay? Okay, so this is the notion, okay? And then again, we have some people out there who don't share this notion or learn something different at their monastery, okay? Here we have, Paul says, mass isn't the quantity of atoms in an object. Okay, so we have a different opinion here. This guy went to a different school, I guess, okay? It is the quality of matter that resists changes in its momentum. Well, no, first of all, nothing in mathematics is qualitative, and mass is considered a quantitative, both mass and weight are considered quantitative parameters. They're not qualitative at all, okay? But this guy raises the issue that it's the quality of matter, some kind of quality. So he says, no one is claiming that the number of atoms in an object moving at an appreciable fraction of the speed of light is going up. Okay, so what are they saying? It says that quality of all atoms in that object is increasing. Okay, so this is another version. You can see people are very mixed up on what mass is. And of course, when you define mass and say it's the quantity of matter, some people don't like it because it destroys their religion. What is it specifically destroying? Well, it's destroying Einstein's notion that if an object moves close to the speed of light, that's what special relativity says, mass increases. Known as relativistic mass, right? Relativistic mass is an object that accelerates, usually in the context of special relativity, accelerates at near the speed of light, and as it approaches the speed of light, its mass increases. So once again, what increased? The number of atoms, which is the rest mass, or is it the weight, how much it presses up against the scale? Okay, which one is mass? These are two different notions. And we usually weigh a person and say, oh, this is your weight. And they say, well, that's the notion of ordinary speech. That's the popular notion. It's not the real super duper scientific notion. Okay, let's find out. Let's keep going. Let's see if we can get to the bottom of this weight mass dichotomy. Okay, here it is. We have, fellow says, weight is a force. Okay, let's find out. Which is a vector. We're going to get into that in a little while, but vector essentially is that little arrow that the mathematicians draw, which has magnitude and direction. Direction being a qualitative concept. Okay, direction. There's no number you can put for direction. You can't say 5 and understand, or 5 units of whatever, and think that that's got direction of any kind. In fact, that's exactly the opposite. When you have 5 followed by a unit, that's usually a scalar, what is known as a scalar. And he says that there. He says it has magnitude and direction, and mass, on the other hand, is a scalar. So what are we saying here? We're saying that in the first case, we're talking about gravitational pull. Okay, and that's what force is, using Newton's equation of force, right? Weight is a force, according to this fellow, meaning it's dynamic, okay, because force is dynamic, okay? And mass, on the other hand, is a scalar, meaning it has no direction, okay? So one has direction, the other one doesn't, okay? What is weight? Weight is the action of gravity on an object. That's what Newton's equation says, okay? But is it a force, first of all, or is it a tension? And I'm saying it's not a force, it's a tension, and tension is not a force. Tension, no one wins the tug of war. Tension does not have direction. Force is a vector, has direction, tension does not. Okay, so the question is, that equation there, mass divided by distance squared, okay, does that have direction? And the answer, no. What we have right there is a static situation where we have two masses, the Earth and the moon. We take a snapshot of that. It's a snapshot right there. It's a static situation, no motion. And at that point, we have weight. What is weight? There you have the equation. The separation between two objects. We're taking a snapshot to calculate that value, called weight. Okay? And what we have is just distance between them. Separation, not distance traveled. No one's traveling. Nothing's moving. It's a snapshot. It's a static situation. All we have is a separation between the center of mass, right, of the two objects. All we have is distance, not distance traveled. Okay, and that's the calculation. Okay, so that is a tension. That's not a force, because there is no motion, there is no vector, there is no direction to tension. It's just a static situation. Think of it as a dumbbell. Okay, two weights separated by a stick made of a single piece. That's tension. When you pull the rubber band to a maximum that you can stretch it, that's the maximum tension. That's called tension, when you can't move it any further. Okay, so the maximum stretch on a rubber band, we'll call that tension. You can't move it any further. And it's like if you had something separating, for example, your two fingers, that's made of a single piece. That's what it amounts to. That's what tension is, and that's what that equation says. There's only distance separation between two objects. Okay, so weight is not a force then, not according to that equation. Okay, because that's not a vector. The other equation, Newton's second law, that is a force, because there is direction in that equation. There is no direction in this equation of force, which is not force, which is tension, and that's what weight is. It's a value for a given location. Weight is location specific. Okay, and so here we have another situation that clarifies this. We have Newton's gravitation equation states that you have weight before anything is accelerated. Okay, weight is location specific, and location is a static concept. Okay, that's what the equation says. Weight, meaning tension, is separation between two masses. That's all it is. And all we're saying is that the astronaut there, he weighs 100 kilograms on Earth. You take him a little farther back, out, and for a given location, no motion, snapshot, okay, separation. He weighs now 50 kilograms at that location. If he moves a millimeter, he's going to have a different weight. So again, weight is location specific. You move him farther out, he weighs only 25 kilograms at that location. He moves an inch, all bets are off. He no longer weighs 25 kilograms. He may weigh 25.1 or 24.9. No longer does he weigh 25 kilograms. Only for a given location with respect to the center of the mass of the Earth, right, does he have 25 kilograms. Okay, do we understand that? And the only way you can explain that is, here's the illustration for that, okay, is because all the ropes, and here we are converging upon him from the Earth. Every atom on Earth is bound to every atom in his body. So as he is closer to the Earth, the ropes fan out, and so he has more weight. He has a greater acceleration towards the Earth at that location. Again, it's an acceleration, but we're talking about a given location in which that 50 kilograms is valid, for example, or the 25 kilograms is valid. Once he's closer to the Earth, obviously he has a different weight. Okay? The only way you can explain this is if every atom in his body is bound to every atom on Earth, first of all. Second, you can see that in this case, I've only put one atom connected to every atom on Earth, or even to many atoms, not even to every atom, because you wouldn't see anything if I put all the connections there. But you can see what's happening. You have more ropes fanning out as you approach the Earth. That's what it's all about. And that explains weight, and shows that weight is location specific. Okay, so yeah, the point here is that weight is not something dynamic. Weight is location specific, and what that means is that it's a static concept. Weight is not something dynamic. You don't have to put something on a scale, except in all these experimentalists who think that it's a question of pressing down on the scale. That's how we measure weight and mass, both of them. We measure them by weighing them, right? Whether here or on the moon. And if conceptually mass is the quantity of matter, we have no idea how many atoms it has, which is the way you would have to specify your result of mass. You would have to say 500 trillion atoms. Then that would be mass. That's the way you would have to specify mass. You can't say mass is measured and mass is 1 kilogram. No, that's known as weight. Okay? And now let's do a little thought experiment that clarifies, I think, even further this whole thing. Einstein said that if you travel close to the speed of light, okay, your mass increases. You say, well, hold it. What do you mean mass increases? Am I gaining more pounds? Meaning, am I weighing more? Am I having more atoms, which would be mass? Or am I just weighing more because as you fall, for example, towards an object, towards a celestial object, say you're falling towards a star, right? Well, you're accelerating because gravity is something that accelerates you towards the center of that object, right? So you're accelerating now, let's say close to the speed of light. Did you gain more pounds? Did you gain more atoms? Or is it simply that your weight increases, that the acceleration of gravity on your atoms is what producing this acceleration, this speed, this increase in speed as you fall towards the object? Okay, so here, let's illustrate what I'm saying here. Okay, picture's worth 1,000 words, where a movie is worth 1,000,000 words. Okay, so let's go with a movie. Okay, so we save a lot here. Here we have two objects. Okay, they're exactly alike. It's the same object on the right and on the left. Okay, and they have the same number of atoms. But as you can see, the one on the left is accelerating faster than the one on the right. And that's because the object on the star, okay, in this case, the one on the left has more mass. Okay, it's got more atoms. Therefore, it's producing an acceleration on the object that makes it go at 99% of the speed of light. And the other one, almost the same, but not quite. It's 95% of the speed of light. Okay, so the only difference here is not the two objects that are falling. The difference here is just the object that's underneath. Okay, the star in this case. And think of it again as the moon. If you take the Grand Pillow from here to the moon, it's going to have a different acceleration. So even though it's at the same distance from the ground that it was here on Earth, it falls at a different rate because the acceleration of gravity over there is different. Okay, so that's what I'm illustrating here. So we have one acceleration that forces this object to travel near the speed of light at 99% of the speed of light. And the other one is falling at 95% of the speed of light. The objects are the same. They have the same number of atoms. Okay, so is Einstein going to say that this is relativistic mass, or are we talking about weight here? Because this is what they illustrate when they say, look, this is weight. The mass is the same, but when you take it to the moon, the mass remained the same, but the weight changed. Okay, so now we have that situation here. Are we talking about relativistic mass, or are we talking about weight? This is the question. And of course, this is something that Einstein never figured out. In fact, no mathematician figured out that what they're talking about is weight. So whenever they refer to relativistic mass, what they're really talking about is weight. We're saying that if an object falls at 99% speed of light, and the other one 95% of the speed of light, they're talking towards an object, a celestial object. They're talking about weight. They're not talking about relativistic mass, whatever mass is. They just created this unnecessary concept called relativistic mass to say that an object accelerates when it goes near the speed of light. Yeah, it's known as weight. We've known that for many years now. Okay, and I guess Mr. Eine never figured that out. He wasn't smart enough. Okay, so we don't know what energy is. Mass is another form of energy. We don't know what mass is because mass is measured. That's how we determine mass. We don't give our results in terms of quantity of atoms. We give it in terms of kilograms, which is a measurement and not counting. There's a difference between measuring and counting. So we don't know what energy is. We don't know what mass is. Turns out power, the subject matter today, has something to do with energy, which has something to do with mass. So I'm sorry to tell you that we're going to be in deep trouble today. We won't know what power is, but let's give it our best shot. Let's see if we can get to the bottom of power, which is another important parameter that they use in mathematics, known as mathematics, or some people know as mathematical so-called physics. Okay, here it is. We went through these different parameters. Force, mass, weight, acceleration, distance traveled, which is not the same thing as distance. Okay, distance in physics is separation. Distance traveled is a parameter that belongs exclusively to mathematical physics because they're going to put a number for that. They're going to tell you in meters or in seconds how far you went, etc. You know, so distance traveled is a measure of mathematics. It has nothing to do with physics. Physics, separation. That's qualitative. Physics is 150% qualitative and nothing but. Okay, we don't use numbers in physics. Okay, velocity, speed. What was the difference? Well, velocity has direction. Speed doesn't. Okay. But then we have the problem when you turn a corner, they want to talk about velocity and they say, well, the velocity changed. Well, what do you mean the velocity changed? Did the direction change? The speed remained the same, but the direction changed. But direction is a qualitative concept, and so we have a problem there because that doesn't belong to mathematics. Okay, so we have a problem with velocity. Okay. Anyways, it's again a parameter that belongs exclusively to mathematical physics. It doesn't belong to science or to physics. Physics, we're interested in explanations and not in measurements or quantitative values of any kind. Work, energy, and temperature. Today we do power. Okay, well, let's see what power is. Let's find out. One good way of getting to the bottom of that is finding out what the definition of power is. Let's find out the definition. Here it is. Power, the amount of energy. Energy, ooh, that's spirit. Transferred or converted per unit time. And there you have one equation. You would think it's the only equation. You're going to be surprised. Okay, so what is it? Power is equal to energy divided by time. Straightforward, easy stuff. Just memorize it. Take the test on Friday and you won't have any problem. You won't get hurt. Okay, but what are we talking about in terms of physics? What is this? Well, energy is the capacity, the ability. Okay, that's the definition of that. So that's what you put. We got to put the word capacity on top of where the E is, right? What is the little t? Well, that's time. What is time? Is what a clock measures. Okay, that's very important because clock is what a device that measures time. So we seem to have a circular definition or argument here. I mean, what have we learned with this? Power equals energy divided by time. We have no idea what energy is. We really don't have an idea what time is. There's no definition. Mathematicians tell you they don't know what time is. And then you have these definitions which are circular. So far, it's like son comes home and father says, hey, son, so what did you learn in college today? And I said, well, not much, Dad, not much. All I did was learn that P is equal to E over T. Okay, great. Memorize it and you're done, Okay, and so it turns out that we have more equations for this same parameter. We thought that power was energy over time, transfer of energy, conversion of energy, whatever. And now we find out that it's also force multiplied by speed, velocity. In parentheses, okay? This is not I took this out of there, okay? From someone else. Okay, so this is from the PhDs, okay? And there's your equation. P equals force times velocity. Okay, so that's a little different than E over T. Now we have F times V, okay? Little v, okay? Big F times V. Okay, does it stop there? No, power is also W over delta T. What is the W? It's work. And what is the delta T? Elapsed time. And then you find other forms of power, other flavors, okay? Electric power. What is that? Well, that's P is power equal to V times I, voltage times intensity of current, or intensity squared times resistance, or V squared over R, voltage squared over resistance. So we have all these equations, they're all power. What the hell is power? I mean, which one of the, will the real power please stand up? Okay, we have all these versions of power. I'm lost already. I wanted to get to the bottom of power, but all I have is all these versions of power, and they call every one of these flavors, they call them power, electric power, and wattage power and work power and force power. They have all these powers. Okay. Okay, let's see if we can improve on that. It turns out it only gets worse. Okay. It says power is a scalar quantity. Scalar? What the hell is a scalar? Well, a scalar is a physical quantity. A physical quantity. See, it's not an abstract quantity. It's a real physical one that you can hold in your hand. It's a quantity that you have there in your hands. That is completely described by its magnitude. Okay? No such monster in physics as a physical quantity. Okay, let's clarify that. What is a vector? Well, it's kind of something extra. And it's a geometric object, it says. Object? What do you mean an object? A geometric object? Vector is an object. Oh, I think they mean an arrow. Like an engine arrow that you shoot. Is that what an object is? That's what a vector is, an arrow? Yeah, it's a geometric object. No, it's a mathematical concept, not a geometric object. No such thing as objects in mathematics, in mathematical physics. Okay? They have no objects. They never defined the word object, so they can't have objects. With both length and direction. Okay, length and direction is not an object. Length and direction do not an object make. Two concepts do not an object make. Okay, so no. If a vector's length and direction, magnitude and direction, we still don't have an object. So don't call it an object. But the point here is that these two notions are different. Scalar is a quantity, and the other one is a quantity with direction. That's the bottom line. That's the difference between a scalar and a vector. Okay, and so let's continue. Let's find out. Maybe we've learned something today. I don't know. Quantities such as force and velocity have both magnitude and direction and are called vectors. Okay, so here we have a scalar. Power is called a scalar. Okay, it says so there, right? What is this power equal to? This scalar equal to? Well, it's equal to two vectors. So we multiply two vectors in this example. Force, which is a vector, times velocity, which is a vector, and we end up with something that has no direction, a scalar. Okay, so when you multiply two vectors that have direction, you end up with directionless scalar. Okay, great. We learned a lot these days. Okay, let's find out if this is true, because it says there, examples of scalars are volume, density, speed, energy, mass, and time. Okay, now we know. Those are all scalars. Please memorize this for the test on Friday. Okay, what are the scalars? Volume, density, speed, energy, mass, and time. Got it? Memorize them? Okay, let's continue. Let's find out. Okay, let's find out if this is true. And we look it up, and it says that time has direction. It's got a little arrow there. It's going up. You see time. This is on the light cone that they call in mathematical physics. It's one of their sacred icons. You got to pray to this. And it has time going up in a direction. In fact, they talk about the arrow of time, and they talk about time having direction. And you're saying, what do you mean direction? Yeah, it's a vector. It's a coordinate. It's got an arrow. That's what that arrowhead points to. It's giving you direction. And the direction is forward. Now, is there such a thing as a forward direction? Okay? Is this the issue? And, who's forward? Your forward or my forward? I mean, what are we talking about when we say forward? And they say, well, to the future. Well, is that a forward? What kind of direction is the future? Point to it. Okay? And then the other one is tension. I mean, is tension a scalar? Okay? Because, again, tension means that you have a single piece thingy that's separating two objects. Or you can say something stretched to the limits, which, again, is a static concept. That's what tension is. Nothing, no one's winning the tug of war. Nothing is moving under so-called tension. And so the question is tension a scalar or is it a vector? And again, they say that tension is a force. Force is a vector. So are we going to say that tension is also a vector? Which direction is tension pointing to? Which again takes us to weight, which is a tension, which is valid for a single point in space. If you want to use that language, we say it's for a single location. Okay, with respect to all matter in the universe. Weight is only valid for a given location in the universe. Once you move that object, it has different weight with respect to every single object in the universe. Known as Mach's principle, everything pulls on you in the universe, or you're bound to everything in the universe. Okay, so I think we're learning a little bit about Maybe not about power, because we still have no idea what power is, but it's a scalar, whatever that is. Okay. Um, we have this thing called power that has no direction, but they have all these other things that have direction, such as tension, which is supposedly a force which has direction, and time, which they say has direction, but they say is a scalar. So you try to figure it out. Okay. Here are the conclusions. Okay, that's all I can give you today for power. Use it more likely in politics than in physics, okay? Because you're never going to find out what power is. What are the conclusions? Okay, power is the transfer conversion of energy, according to their own words, where energy is an adjective or adverb. Power is a scalar, no direction, okay? Made of quantities like force and velocity, which have direction. Yeah, you can have different directions for this, and they could cancel out all that stuff. It doesn't matter. My point is that here you have this thing, power, known as a scalar, but it also has the word time in there, which they say, well, it's a scalar, but it turns out time does have direction, according to mathematical physics. And then you have weight, which again they say is a force, which is supposedly a scalar, but it turns out weight is a tension, and tension does not have direction. So those are things that the mathematical physicists never discovered, because they do equations, but they don't understand the concepts, the physical concepts that underlie the concepts that they created for mathematics to do measurement and numbers. Okay, power is made of time, which the mathematicians claim is a scalar quantity, but this one has direction, okay, because they claim both, that it's a scalar, but that it has direction. So now we don't even know what a scalar is, because a scalar supposedly is a number without direction. And then, like energy and mass, there are several types or flavors of power. So you figure out what power means or is. Okay. Corollary, power is another convenient and powerful word of mathematical physics, mathematics, right? That describes everything and explains absolutely nothing.